All right, let's talk about a classic physics problem. You know the type, one that looks absolutely impossible when you first see it. We're talking springs, masses, gravity, things flying all over the place. But what if I told you there's a secret hidden inside of it? A secret that makes the whole thing surprisingly simple. Let's dive in.
So here it is. This is a problem straight out of the famous Irodov textbook, number 1.150 for those of you following along. And you can see why it stumps people. We've got this whole system, and we need to figure out its motion. But just look at all the pieces moving around. It honestly looks like it was designed just to be confusing.
And just look at this chaotic setup. You've got two spheres, they're tied together by a spring. Right at the beginning, at time 0, they get launched with their own separate velocities. So as this whole thing is flying through the air, the spring is stretching and compressing, making the spheres bounce back and forth, and on top of all of that, the entire system is falling because of gravity. It is, in a word, a mess.
And this is right where your brain might just freeze up. I mean, how on earth are you supposed to track all of that? The force from the spring is changing constantly. The velocities of the individual spheres are all over the place. So do we have to bust out some insane differential equations to figure this out? Well, what if I told you there's a much, much easier way?
See, the secret here isn't to get bogged down in every tiny detail. It's all about changing your perspective. It's about figuring out what actually affects the system as a single entity versus what just creates all that noise on the inside.
Now, I know that sounds a little crazy. The spring is literally right there yanking the spheres back and forth. How can it not matter? But for the two very specific questions we need to answer, what's the total momentum and where's the center of the system going, that frantic action from the spring is, believe it or not, completely irrelevant. Let's find out why.
And that brings us to one of the most powerful concepts in all of mechanics, splitting forces into two distinct groups, internal and external. Think of it like this. Internal forces are like two people arguing inside a moving car. It might be loud and chaotic inside the car, but it doesn't change the car's speed or direction. External forces, on the other hand, are like someone pushing the car from behind. That is what actually changes the overall motion of the car.
So let's apply that idea to our problem. The spring pulls sphere 1 towards sphere 2, and thanks to Newton's third law, it also pulls sphere 2 towards sphere 1 with a perfectly equal and opposite force. So for the system as a whole, those two forces add up to 0. They cancel out. They're an internal force. But gravity? Well, that's the Earth, a body outside our system, pulling on both masses. That's our external force. That's the one that's going to change where this whole thing goes.
Okay, now that we have that crucial insight, let's go solve the first part of the problem. We're going to find the total momentum of the system as it changes over time.
And right here is where you see the magic happen. There's a fundamental law that says the change in the system's total momentum depends only on the total external force. We get to completely, 100% ignore the spring. So the only external force we have is gravity, which is just the total mass, m1 plus m2, times the acceleration g. To find how momentum changes with time, we just have to integrate that constant force. It's that easy. And what we end up with is this beautifully simple result. The total momentum at any time t is just whatever momentum the system started with, which we call p of 0, plus the steady push it's gotten from gravity over that amount of time. It's a clean, linear relationship, no chaos here. Let's just break this down. P of t is what we're looking for. P of 0 is just the initial momentum of both spheres added together, which we were given. And that second term, that's just the impulse, the accumulated kick from the constant force of gravity. Notice what's missing? There's no spring constant, no mention of oscillations, just clean, simple physics.
Okay, part 1 is done. Now for the second part of the question, finding the position of the system's center of mass. And trust me, this is where the simplification gets even cooler.
So the center of mass, it's not a real physical thing. It's a calculated point. But it's an incredibly useful idea. The motion of this one special point is determined only by the external forces acting on the whole system. It behaves as if you squished all the mass down to that single spot, and it completely ignores all the chaotic internal forces, like our spring.
So all that crazy bouncing and stretching and compressing that the two spheres are doing, the center of mass doesn't care. It doesn't feel any of it. It just sails smoothly through the air as if the spring wasn't even there. This trick transforms our impossible-looking problem into maybe the simplest problem in the whole textbook.
And here's how we do it.
The total mass times the acceleration of the center of mass equals the total external force. Well, we plug in gravity for the force, and look at that. The total mass, m1 plus m2, is on both sides, so it just cancels out. The acceleration of our special point is just g. It's just the acceleration due to gravity. This means our center of mass moves exactly like a single ball you just threw in the air. It's a standard projectile motion problem, something you've probably done 100 times.
So there we have it. By focusing on the system as a whole and by carefully separating the internal forces from the external ones, we've found our answers without ever having to get our hands dirty with the messy details.
And this is the most crucial takeaway. We didn't need to know a single thing about the spring to solve for the system's overall momentum or the path of its center. We just had to look at it from the right perspective, and all that complexity, it just melted away. That, right there, is the elegance of physics.
And this really highlights a common trap for students. When you see a complicated problem, your first instinct is to try and calculate every single detail. But so often, the real skill is in recognizing what information is just noise. In this problem, everything about the spring, its stiffness, how much it stretched, it was all just a distraction from the simple, external physics that was really in charge.
You know, understanding this distinction between internal and external isn't just a clever trick for one problem. It's a fundamental tool you can apply to almost any system in mechanics. It really is like gaining a new physics superpower.
You should burn this idea into your brain. Before you jump into writing equations for any problem, just stop for a second. Define your system, identify all the forces, and ask yourself, which ones are internal arguments and which one is the external push? Getting that straight from the start will save you a world of pain.
And this isn't just for weird spring problems. The exact same principle is at work everywhere. The forces between two colliding billiard balls are internal. It's what lets you predict where their combined center of mass will go. The gravity holding a galaxy together is internal. It's the pull from other external galaxies that determines its path through the universe.
So I'll leave you with this question to chew on. Think about a firework exploding in the sky, or a diver twisting and turning in the air. Where else can you find this amazing simplifying principle at work? Once you start looking for it, I promise, you are going to see it everywhere.